Single slit diffraction. Here we have water waves passing through a gap, and in this case the gap is a similar size to the wavelength of the waves. You see that the waves spread out, and this is known as diffraction. When the gap is much larger than the wavelength of the waves, there is less spreading, as you can see in this diagram. So we see the wider the gap relative to the wavelength, the less the wave spreads. Here we have an arrangement to get a similar effect with light. Sending light through a narrow slit towards a screen, we would observe a pattern something like this. So we have a wide, bright fringe in the center with a dark fringe either side, and moving out then we get a narrower, less bright fringe, a dark fringe, and a less bright fringe still moving further out. If we plot a graph of intensity against position along the screen, we get something like this, with a very high intensity in the center, going down to 0, coming up again for the first bright fringe, down to 0 again, and up again for the next bright fringe, with the same thing on the other side. Just a few things to note about this pattern. The central fringe is twice the width of the other fringes. The outer fringes are all the same width. The intensity of the fringes decreases with distance from the center, and the central fringes are much higher intensity than the outer fringes. As with water waves, if the slit gets narrower, or if the wavelength increases, the pattern will spread out more. So this represents the slit getting narrower, and you see the pattern is spreading further. This effect can limit the resolution of optical instruments such as cameras, and even the eye, due to diffraction of the light as it passes through the pupil. A telescope has a wider aperture than the pupil, and so is less affected by diffraction, and therefore has greater resolution. This means a telescope is more able to separate the images of two very close stars than the eye would be. Here I've tried to show the effect of sending blue and red light simultaneously through a gap. I've raised the blue relative to the red just so we can see the difference between the two. You see the blue light has produced a narrower central image. This is due to the shorter wavelength of the blue light. Also, the first bright fringe to the left for the blue is not as far across as the first red fringe. It's also narrower than the red fringe. Again, this is due to the shorter wavelength of the blue. This is the second blue fringe, and you'll see the second red fringe is much further to the left still. I've related that down here with the intensities of the red light and the blue light. So we see the red light would produce wider bands than the blue light due to its longer wavelength. Microscopes can be fitted with blue filters to reduce the diffraction effects they would get from the longer wavelength light.